Okay, another way that we're going to be looking at to calculate enthalpy change is by using what's called Hess's law. And Hess's law is like using little tiny puzzles in order to solve for enthalpy change. Now, looking at this definition, it sounds very confusing, so I just want to kind of like summarize what this is trying to say. Hess's law basically states that if chemical equations could be added together to equal another equation, the delta H's can also be added. And we're going to illustrate this idea with some examples, so if that doesn't make a whole lot of sense, when you see Hess's law applied, you'll see how this works.
So the first thing that you need to be aware of is that enthalpy values, based on stoichiometry, depend upon the way that the reaction is written and also the phases. So in this first reaction here, we have hydrogen gas reacting with oxygen gas to produce water in the gaseous form. And the delta H for that is negative 242 kilojoules. Now, if we take that reaction and we multiply it times 2, so we have 2 hydrogen, 1 oxygen making 2 waters, the delta H is going to be twice as large. That's because stoichiometry tells you that if you increase the amount, you're going to increase the energy. If we reverse that reaction and have the water decomposing to form hydrogen and oxygen, then our delta H is going to be the opposite of the first one. The first one had us forming the 1 mole of water, now we're decomposing 1 mole of water. So the magnitude is the same, but the sign is going to be opposite. And in this last reaction, we have what appears to be the same reaction as the first one, except for we're making liquid water instead of gaseous water. And again, the enthalpy values depend on the phases of the reactants and products. So this one has an energy change of negative 286 kilojoules. So when you are manipulating reactions in order to use Hess's law, you have to remember to do the same thing to the delta H value.
Okay, so let's look at a simple example. Okay, so usually you're going to be given the reactions that you're going to be adding together and the final reaction that you're trying to obtain. So in this case, we have our first reaction where we have carbon dioxide in the gaseous phase, and it's decomposing into carbon monoxide and a half a mole of oxygen. The delta H for this reaction is a positive 283 kilojoules. And then we have a reaction for carbon in the solid phase reacting with oxygen to produce carbon dioxide. The delta H is a negative 393.5 kilojoules. Now this is telling us that these two reactions somehow can equal the reaction we're trying to find, which is carbon in the solid phase reacting with a half a mole of oxygen gas to produce carbon monoxide gas. And we want to find the delta H for that third reaction. Now the way I go about this is basically trying to figure out how to make the reactions I'm given match up to the reaction that I'm trying to find. And so I start with the reaction that I'm trying to find. So I would look at the very first element. So I'm going to look at the carbon or the first molecule. And I find it in the reactions that I have I have a given delta H for. So if you look at the second reaction, I have the same carbon in the solid phase. So I'm not only looking at the element or the molecule, I'm looking at the phase to make sure that they match up. I check for quantities. Okay, so I have 1 mole of carbon in the reaction that I'm trying to find the delta H for, and I have 1 mole of carbon in the reaction that I'm given the delta H for. So I'm not going to make any changes based on that atom. In the second reactant in the unknown delta H reaction, I have a half a mole of O2. Now, I'm going to deal with this one in just a second because you're going to see how that kind of works out. But what's complicated about the oxygen is I have oxygen in both given reactions. So if you have a molecule that's identical on opposite sides of an arrow, those actually subtract or cancel. So that's going to work out that I'll end up with a half a mole of oxygen on the reactant side because in the reactions that I'm adding, the half a mole is on the product side and then a whole mole is on the reactant side. And if I look at the product, my product is the carbon monoxide. And again, I'm looking for location and quantity, and the carbon monoxide is a product in the first reaction, and I have 1 mole, so I'm not going to make any changes. Now, these are like adding algebraic equations, so I'm going to essentially add the two reactions that are given and see if I can make it equal the reaction that's below. So things, again, on the opposite side cancel. So CO2 is a reactant in my first reaction It's a product in my second reaction, so you're going to see those are going to cancel. Oxygen is going to cancel, but be left with a half a mole. And then carbon monoxide stays the same. Now, if I was just to look at this reaction and write it, you would see I have left carbon plus a half a mole of oxygen, and that's going to make carbon monoxide gas. So you see that's the reaction that I was trying to find. So since I was able to add those two reactions, I merely am going to just add the delta H's. So it's going to be 283.0 plus a negative 393.5. So that's going to equal negative 110.5 kilojoules. And adding significant figures will tell me that I'm going to have the 1 decimal place. Okay, so let's try a more complicated example.
Okay, in this example, we have reactions involving sulfur and oxygen. The first one is sulfur dioxide gas decomposing to form solid sulfur and gaseous oxygen. Delta H is 296.8 kilojoules. In the second reaction, sulfur trioxide is decomposing to form solid sulfur and oxygen. And the delta H for this is positive 791.4. So both of these decomposition reactions require energy. The reaction I'm looking for is 2 sulfur dioxide plus oxygen yields 2 sulfur trioxide. So let's take a look at the first reactant. The first reactant is sulfur dioxide, and I have 2 of them. I can find sulfur dioxide in the first given reaction, but there's only 1. It's on the correct side, but it's not the correct quantity. So in order to get the correct quantity, I need to multiply that entire reaction times 2. And since I multiplied the reaction times 2, I also have to multiply the delta H times 2. So my delta H is going to be 593.6, and that's a positive value. In the second reaction, well, let's go back and look at the one I'm trying to find. Again, we have oxygen in 2 different reactions, and when you've got something that's in 2 different reactions, you want to hold off till the end because usually it works out. So I'm going to go to my product in the reaction that I'm looking for, and I'm making 2 moles of sulfur trioxide gas. In the second given reaction, I have sulfur trioxide, and I have the right quantity, 2 of them, but it's on the wrong side. So what I need to do with that reaction is flip it. In other words, I'm going to write it the reverse of the way it is here. So I'm going to have 2 sulfur solid plus 3 oxygen gas yields 2 sulfur trioxide. Now when you do that, since you reverse the reaction, the sign of the delta H has to be reversed because the delta H for a reaction is equal in magnitude but opposite in sign to the reverse reaction. So that second delta H becomes negative 791.4. And then all we have to do is add those 2 delta H's together, assuming that the reaction's complete. Let's go back and make sure that we did this correctly though. So I have 2 sulfur dioxides on the left. I have 2 sulfur dioxides in what I'm looking for. I have 2 sulfur trioxides on the right. And when I flip that reaction, I had 3 oxygens on the left and 2 oxygens on the right. So the oxygen on the right will cancel, leaving me with 1 on the left. So what I was looking for is what I actually obtained. So I can just add the 2 delta H's together. So it's 593.6 plus negative 791.4. So the answer that you get is negative 197.8. I know some of you are probably thinking about where are these delta H values coming from. you'll be given delta H values that are needed if you're going to use Hess's law. So don't worry about where that 296.8 came from. That's going to be given to you. And there is a way that we can actually calculate those, and that's going to be our last podcast for this unit.